Hello and welcome back. My name is Corey and you're my rubber ducks, I guess. And this is the series where we are creating a new programming language from scratch using C++, modernish C++, tools like Flex and Bison and ICU. And of course, our editor is a terminal window and Vim. This is 100% live coding, which means you see all of my mistakes, but you also see all the progress. You see me talking through the errors that I run across. I am not copying and pasting code. I am creating it in front of you, and that means, yes, sometimes I have to go back and change things that I've done before. As I've always said, there's nothing up my sleeves. I am just bare and exposed in this, and you see all the good stuff I do and the bad stuff I do. So where are we? Well, episode, what did I say this was? I think 44? Yeah, episode 44. All right, and if I say, there we say, so git log, the last commit was the end of episode 43. We've seen that, all right. But if I say git status, you will see that there is a difference in tang.hpp, but this is in our to-do list. So if I say git diff, you'll see I removed some of the things talking about array access and just moved the slice out to its own bullet point. We're not going to be doing slicing yet, but we are going to be cleaning up some stuff. So for the moment, I'm just going to say git commit, and what are we committing? Just update master to-do list, removing array stuff. Sounds official. All right, so what did I put on the title slide for this? Basically, we're going to be working on the garbage collected container that we have. And so on the right hand side, we will go ahead and do our make clean and make test, and just so it's going to be watching for our changes. And I think the first thing that we're going to do, let's edit the include for garbage collected and our source for garbage collected. First change I want to do isn't that big of a deal. We have a template here for this make command, and it's a static function. That's 100% fine, not going to hurt anything. However, everything else, the copy constructor, the move constructor, the copy assignment, move assignment, and the destructor can all be moved out. And that's what we're going to do. We're going to just move all of these out. So there we go. I've yanked them. And now in my CPP file, that'll be fine. Okay. Just changing the indent. I don't need this text anymore, but we will have to add garbage collected ::. So let's get a copy of that and start putting that in place in the different oh no, that should go there, there, and the destructor, there we go. All right, remove comments that are not needed anymore, or Doxygen comments, I mean to say. That's fine, and it's not going to like it because it's going to say, oh no, they're already defined. Well, not anymore. We're about to remove those. D4, D5, D10. Oops. There. Just opening all of those folds because they don't need to be folded. And now there we go. That's what I should be doing. Just have to find the right button. And the answer is a capital A. Will put me in insert mode at the end. And so now the only thing that this should have... Oh, didn't do the destructor. There shouldn't be anything else in here. There's not. Save it. Everything should still compile correctly. The only reason they weren't in their own file in the first place is because I originally was trying to do it as a big one template for the entire class, and well, that didn't work, and I just never fixed this. So sometimes you got to go back and take the time to fix the things that you've overlooked or you've been putting off. So that's fine. All of our tests are passing. It's always a good thing. And let's then, just those two files are changed. Our diff is what we would expect. That's good. So our commit is going to be refactor garbage collected move. Is it declarations or definitions? Oh, I always forget it. I believe we moved the declarations to from .hpp to .cpp. There we go. Simple enough. All right, let's go back because there's another thing that I want to do. I want this has to do with efficiency. So we just added the ability to pass by, and this is in the previous episode. We added it, added the ability to pass by value instead of by reference. And so if a variable is passed in as an argument, then it will be overwritten. The problem is now that could cause a lot of work, and we want to not have to create new copies of these garbage collected values unless we absolutely need to. So it should be possible to ask the garbage collected value, hey, do you need to have a deep copy made, or is it okay to just copy you over? Why? Because, well, a garbage collected integer can't ever have its integer value changed. We just get a new integer. We just get a new garbage collected value. So, and even in the, wait, is that true? I'm thinking about this. So when we do an assignment, it does a poke and that overwrites. Is that right? I'm glad you asked. Let's look. So if we edit the source program execute, vim source program execute. I was trying to do the vim command. And the assign command. There we go. We get the index from the stack back. Oh, sorry, that's the assign index. Where's assign by itself? Oh, we don't have an assign. We use poke. There we are. So all that we do is we get the position and we use an equal sign. So what happens with a garbage collected operator equal? Okay, well, we can do that by looking up the garbage collected since I'd already opened those. There we go. For the operator equal, this is the .hpp. So here's the .cpp. So for the operator equal, this is a copy. And what we're doing is we're calling our destructor and then we're stealing the resources. This is a copy assignment. And I should be saying, we want to go and make sure that there's no other, that we haven't overlooked anything here. So this is a copy assignment. We get rid of everything that we do and we replace it with the other garbage collected. Well, we point to the same things. Our ref points to their ref. Our count points to their count. And then we increment the count. And our recycle now points to their recycle. Why? Because then when the this other one goes away, yeah, we're keeping the count correctly. Because when it goes away, it will decrement. Okay. This is the move assignment. And all that we do is, again, we call our own destructor. So we never modify ours. So we never modify these values. The only time that we modify is actually in the assign index and an assign period, which will be the dot operator, period operator, when we deal with objects later. So we're never overriding. That means that, yeah, we should be able to say, we've got make a copy, but we should be able to say, do I need to make a copy? So let's do it here. Determine whether or not a copy is needed. All right, and for this, it's going to at return whether or not a copy is needed as determined by the reference. That's too long. That's okay. Computed expression. So we're going to pass to that, if that gives you an idea of how we're going to do this. And so it's going to return a bool, and that is how about is copy needed? And it will be const. Okay. And now, instead of make copy, we're going to have this garbage collected is copy needed. And all that it's going to do is it's going to return this arrow ref is copy needed. So it's just going to pass it through to the ref. All right. Now, that computed expressions don't have that, so guess what? We're going to have to add it for computed expressions. So our include computed expression.hpp and our source for computed expression.cpp. That's fine. In fact, we can just copy is copy needed. We've got make copy. Here we go. Determine whether or not a copy is needed. I think I want to do it this way and say copying is only required for containers is only required for computed expressions which serve as containers, such as computed expression array and computed expression I was going to say computed expression object. I'm not exactly sure that I like computed expression object. I may put it. But we've got this is copy needed. And now we need to create it. We're going to say false. That's our default value. Request a copy of the, what I want to say, there. Okay. See if it likes that now. We should be okay. We're not using this yet, but we're about to. All right, so now I'm exiting because I want to know where do we use make copy. So if I go into source and say git grep -in make copy, where is this used? I'm not as worried about the function expressions, but right here, make copy. So computed expression array and garbage collected. And program execute. Okay. So we're going to go into this. We're going to say computed expression array, garbage collected, and program execute. So the make copy is what we're looking for. And so this is in the array. And we're going to make a copy of ourselves, but we don't need to make a copy. So all that we need to do is say item arrow is copy needed, and if so, item make copy, else item. That should compile. At one point here, I'm expecting a test to fail. So the make copy here, garbage collected, is it should only be. Now, if we specifically request a make copy, let's always do a make copy. Okay, so I think I'll leave that one. But this one, so op copy, now if we say copy, is that okay to do it that way? I'm sorry. I know. I just kind of stopped. It really, what we should be saying is is equal to FP plus position. And you say, Corey, that's longer. Yeah, but we're not redoing the math, even though that's probably being target position. So what we need to say is stack target position dot is copy needed, and if so, make a copy, and if not, it wouldn't make sense to copy it to ourselves, so we can say if all right, so the target position is FP plus position, stack target position. So it's going to be part of the copy opcode. So I don't think our tests are going to fail now. I was thinking that the check is happening someplace else. This is a runtime check to decide do we actually need to copy it, and this could be very helpful to say, yes, I'm thinking I need to copy whatever it is I'm passing in, but because it's a number, I don't need to copy it. All right. So now, actually, I do think our test is going to fail because now we're never copying because we've never told it what it needs to copy on. Yep. So that one failed. Good. That's what I was trying to explain. Now let's make it not fail. And that is for edit our source computed expression, not source, include. Computed expression.hpp and include computed expression array. Now, why did I open just the regular computed expression? So I could copy this is copy needed. And now, right before make copy, there we go. And this is going to be an override. And now it's going to say, it's not here. Wait. Should be. Did I just do something stupid? It's copy needed, const. This says, why does it say it's not overriding it? I'm just going to go ahead and write this. Bool computed expression array is copy needed const return true. But it's like I made a stupid copy paste mistake and I'm not seeing where it is. So computed expression.hpp has bool is copy needed const. That's a computed expression. Now, if I go to computed expression array, I've got that's why. And that means in my before, this should be virtual. That's what was missing, the virtual. I was like, I know I'm doing it right. No, I wasn't. But I think now our test should pass. Because we will be copying the array and not copying anything else. Again, tests are nice for making sure you don't break stuff. Okay, this one didn't pass. Oh, I got a segmentation fault. Ooh, that's not normal. Anytime that happens, might as well just redo it. But I want to open the I paused the thing here. I just want to see what file that or what test that was. The null failed? That's weird. Didn't it say 17? Our very first test failed? Oh, no. Never mind. That's what it was. It needed to... Because I probably have a missing dependency somewhere, and switching it to a virtual changed the way the class is defined, so something was not getting a link correctly. Okay, that fixed it. Our tests are all passing. That's good. All right. So, got a lot of changes. Git diff. We added our is copy needed. Oh, wait. Yeah, so if it doesn't need to make a copy, it's already on the stack. It's just the copy would have replaced it. This says only replace it if I really need to. Yeah. All right. And this is now we'll say opcode copy only copy if the computed expression says that it needs to be copied. Okay. Not include Tang. That's what I'm looking for. Nope, I should have been an include. Tang.hpp. All right, and I want to look here. So for the strings, we're going to have to start that pretty soon, and that's going to take a lot of work, getting the substrings and all of that. For the default printing, that's going to make more sense as we get into the ICU string. So that's not, yeah. Oh, here's the other one. Garbage collector refactor. Recycle should not call realloc. That's what we want. So, how do we do this? Let's go back into, we're going to edit our source, not computed expression, garbage collect. No, so let's do include garbage collected and source garbage collected. So what I'm looking at is when we recycle something. So where is the recycle? The recycle is up here. we call the deconstructor and, oh, we just call the recycle thing. Alrighty. Oh, that goes to the object pool. Sorry, I said garbage collected, but it's the object pool that that we don't want that on. Okay, so instead, let's include Vim the singleton object pool, and so it's only a .hpp file. All right, because the template's on the entire class. That's fine. And the reason is, oh wow, I wrote this stuff at the very beginning and over a month ago. And I've written a lot of code since then. So what's happening is we have, if I move down to the private variables, we've got the copy constructor is just being hidden. The constructor is hidden from being directly called. We've got our allocation, that it's a C array of allocated blocks. Each contains grow, whatever that is defined as, objects. We've got recycled pointers to objects. And this is what I want to do away with. I want to do away with recycled. But, so we've got our index into allocations representing the current block supplying non-recycled memory addresses. Okay. And the current index within the most recently allocated block of an available pointer to the type. If current index is equal to grow, then a new block needs to be allocated. All right. Now, instead of recycled, we need this is getting a little bit more complex. What I want to do, I'll go ahead and tell you, is right now we're doing a malloc for a block of memory, and then we do another malloc for keeping track of all of the would that work? Sorry, arguing with myself. What I was going to say is we could use the same allocation size or the same allocation block and use the first part of it for the objects and the second part as all of the pointers. And I know we're mixing our types, but it should actually still work. And so at this point, I'm 38 minutes in. I may be breaking this entire thing. But in order to do this, what do I need? I've got current allocation, which is the current block supplying non-recycled memory addresses. So that's just an integer. And I've got current index. And that is, yeah, so where I am. So if I've got an allocation here, an allocation here, an allocation here, the idea is in this singleton thing, I'm never going to use fewer because I always recycle and I never shrink my supply. That's the way that this singleton thing works. And it's just as we get done with stuff and recycle them, then I need to keep track of the fact that they're recycled. But I realized, and I realized this several weeks ago, I just haven't come back to this until now because, well, refactoring time, yay. I realized that in my trying to recycle something, I am calling a memory operation a realloc, and that could fail. And I don't like the fact that that could fail. So what I would rather do is I would rather use the first allocation, a one-time allocation to allocate the memory block, and allocate enough space to keep track of all of the things I'm trying to track, the size of all of those, as well as the recycled things. And then if I need another block, well, I'm going to need the same amount again. So let's see if this makes sense. So recycled size, what I think I'm going to do is I'm going to copy these 12, put them here, and then recycled size is going to go away. I'm not getting rid of it yet. I'm doing this to keep... Yeah, I'm doing this just so that I know what I need to get rid of. Okay, so this is going to be, instead of current allocations, this is going to be current recycled allocation, current recycled index. And so this is going to be index into allocations representing the current block tracking the recycled memory addresses. All right. And then this is the current location within the most, within the current recycled allocation block of an available T star. If current recycled index is equal to grow, then we must move to the next recycled allocation. Okay. So it's not going to like that because I deleted stuff that shouldn't be there. Or I deleted stuff and now it's saying, hey, it's not here. So I've got current recycled allocation and current recycled index. That's fine. For the private, the current recycled allocation is going to equal, we're going to do this the same way, -1, and current recycled index is going to equal grow, because we're taking the exact same philosophy as this. And we no longer need this recycled thing. Is that right though? Can I do it this way? Can I redefine memory? Is it going to complain? We're about to find out. Oh, stuff is going to break big time, by the way. Good. Stuff is breaking. I don't want it to not break. All right. So what do we want to do? We want to for getting, is this the best way of doing it? I know, I'm... Okay. Get. If there's a recycled object, return it first. No changes there. There was a recycle. See if there is an allocation pool memory. Okay, so that. There's not any allocation pool memory, so we need to allocate more. But the goal is to do plus size of t not t, but a pointer to t times grow. So this new block is for each item, I'm also allocating a pointer that will eventually point to one that's recycled. So ultimately, if I allocate enough for 1,000,000, remember the way I wrote this, the allocations never go away, they just get recycled, and I never shrink that because they could be all over the place out of order, and I don't want a lot of memory operations. But I could allocate 1,000,000, and at the same time, I'm allocating spaces for the pointers. All right? Now, these should probably be const exprs and things like that. We'll get there. But, so if the malloc doesn't fail, then we're fine. New allocation is... What is this? Oh, this is keeping track of... so allocations, I'm just making it larger by 1 page. And it's just, these are small, so it should pass. The allocation succeeded. Wire up all of the pointers. Okay, great. Now, the problem is we skimmed over something, and I knew we were skimming over it. And that is if there is a recycled object available. And it's that recycled open. So line 44. I'm jumping forward so I can see what our recycled open is, it was a count, and so so we've got current recycled allocation, that's going to be an integer. That could be -1 if there isn't any. And then current recycled index. That should go from 0 up to grow. All right. Current recycled allocation, current recycled index. So we're going to write new code. If current recycled index and I need to make sure of which one I'm doing. It needs to be allocation because current recycled index. No, current recycled allocation. Because that could be -1. Okay. Current recycled allocation does not equal -1. That means we've got something, I think. Yes. So what I'm doing is I'm going to say this is a pointer to a pointer, and I'm going to cast it as a void star. See if it's going to let me do this. I will tell you my theory. I don't know if it's going to work. My goal is by saying, okay, so this allocations, so current recycled allocations is not -1. That means I've got some recycled number. I mean, I've got something there that I can use. And so I'm going to this allocations, and that is a list of all the allocation pages. I'm going to the current allocation. I'm going to size. Now remember, each one has size elements, but it is size is actually like one past the end. And I'm going to tell it that it's a void star. And then I'm saying, no, it's really a pointer to the whatever type it is. And then from there, say, let's say recycled is equal to that. Okay, so now T star temp is equal to recycled sub this Do I want to do it this way? Yes. Not recycled open, but current recycled index. Okay, so I'm shrinking down the index. Now I need to say, and if this current recycled index is less than 0, and that may never be, if that's a size t, so it should probably be an int. Probably should be an int. I'm on line 47. Okay, we're going down. Okay. Because I don't think a size t, I think it's an unsigned, so it can never be negative. But if it's less than that, then we're going to say this current recycled allocation minus, well, and this current recycled index is equal to, should point size minus 1. I'm just going to save this. It's probably not going to like something. Oh, size is not declared. Of course it's not. It's called grow. How did I get size out of that? I don't know. Because I was thinking of size t. I'm just hoping now for invalid cast from type Oh, that's why. Well, void star 2. And I'm wondering if I just explicitly say, no, this is a T star star. If it's going to complain. It might. I know there's other issues here that are going to do it, but we got past that. It's just saying, hey, you're not using temp. Okay, fine. because we should be saying return temp. That's fine. So it got past this. All right. So now when we recycle something, we've got it so that we're allocating everything. Okay, that's fine. I mean, we're allocating enough space. And now the recycle. Oh boy. The current recycled block. So in case you're wondering, this recycled open, recycled size, all of this is basically broken because it's using the recycled open and stuff. So do I have a cert available here? What line am I on? 105? What's the name of my variable? Current recycled allocation is not -1. That's what I want to assert. Does not equal -1. All right. Now, all that we need to do is, we don't need to do any realloc. We just need to say, how do we get there? So I've got to go back up to where I was doing all that fancy stuff. So T star or recycled now is a pointer to pointers, right? So I should be able to then say recycled sub this recycled index plus plus is equal to obj is what I'm recycling. And then if this arrow current recycled index is equal to grow, then I need to, what do I need to do? Index is equal to should it be -1? Maybe. Well, I'll look in just a second. And then I need to increase this current recycled allocation. Okay, so I want to double check some stuff here. I've got current allocation, current index, current recycled allocation, current recycled index. When I do an allocation, when I do a get, I want to follow the same logic. So I say if it's less than grow, and I implement current index. But once it's equal to grow, so the problem with this is it's always increasing. Monotonically increasing. Yeah, you can use those fancy words. And whereas our recycle is like grow and shrink, grow and shrink, grow and shrink. So if we have nothing available, the current recycled allocation is -1, but if it's not equal to -1, all right, so what we're doing here in the get is we're saying wherever recycled is, and that's following through the allocation pages, and it's starting at where the other thing ends. So anyway, yeah, it's doing that, and then it's saying current recycled index is -. So if it's 0, then it'll drop down to -1. And if it's less than 0, we set it to grow -1, so 1023 if it's if grow is 1024. So current recycled index is the one that should be it's pointing to the last one available. The last one available. So when I recycle something, okay, so I'm going to add that, in fact, down here so I don't have to think about it again. Of an available current location of, instead of an, I'm going to say the last available T star. Okay. So what does that mean it gets initialized in? Current recycled index. What does our current recycled index should not be grow. Should be -1 maybe? Because we don't have any available. Okay, so when we recycle something, we can't just grow it. We want to say okay, so if that is what? If that is equal to grow, then index is equal to 0, and we're going to increment that. Now, okay. So now what are we doing? Okay. Asserting that it's not equal to -1. If it's -1, that means nothing has ever been recycled, or we have nothing left. If current recycle index is equal to grow, I'm recycling something, so I'm incrementing it. And I'm saying, hey, once I increment it, if it's equal to grow, then I need to set it to 0 and go up to the next block. Now, recycled is going to use that allocation block, and I'm going to set the index, no longer a plus plus, just the index to the object. And I no longer need that. I believe that solves it. Now I want to go back and make sure that my logic for the so that's in the recycle. I want to make sure that my logic is correct for the get. So in the get, what it does is it says if there is a recycled object available. How do we know if it's available? Well, if it's not -1, if the allocation block is not -1. All right. So at that point, we now say, that's 45. I want to copy this same, get the block of recycled pointers, because that line is kind of ugly. There. Get the block of recycled pointers. Get the pointer to be returned. And then we'll say decrement the recycled and adjust if necessary. All right, so when I did this, the recycled should be a post, because current points to the current good one, and now I'm decrementing it. So if it's less than 0, decrement that, and we're going to set current recycled index to be grow -1. So let's go back to the idea of when the first time that I recycle something. I need it to be instantiated as grow -1. That's what I wanted to see. So let's go down to our private stuff, and the recycled index is, I was right in the first place, I think, or close, grow -1. I'll worry about the assert later. I may have to clean this and then rerun it. All right. And this should be in the destructor if... Yep, good. In the destructor, you say, why good, Corey? Well, yeah. Why good? Because I was expecting it. So all this does is it frees allocation pages. Frees... Yeah. So as you know, our title was that it was doing some garbage collected cleanup, but this is actually the singleton object pool. Segmentation fault. Oh boy. That's always great. Start from scratch just in case. So we thought we were going to get done early today. Well, I did too. Now we just hope it works. Nope. Probably caught in an infinite loop. And so the easiest thing to do would be to run build apps. Where is this? Test singleton object pool. So it's in the reusing. Well, it makes sense. All right. I'm going to turn on my fan. It's getting a little stuffy up here. Probably doesn't help that I'm wearing a sweater, but hey, it was Sunday today. So we never got out of recycled object is reused. So let's edit the test. And we don't know which one of these, but we do know that we're calling recycle, and it may be the fact that get that this is the first time that there's something that has been recycled. So let's look at get first, because that's my gut reaction of, hey, this is probably where we need to look. And I could be wrong, but okay, if there is a recycled object available, so current recycled allocation does not equal -1. If that is the case, now the only thing that worries me is the fact that it seems like it's caught in an infinite loop, and I don't have any loops in this. go back to the test. Then the test isn't using any loops. I mean, there's this one that's inserting and, you know, but we're not to that yet. In fact, it says that there's 2 tests for recycle, and we're only on the first one. Recycle object is reused. We're not to works after a large number of allocations. So after we So the first time it's called, recycled index should equal grow. That, and then this. So grow was initialized to be -1. Can I do this? See out here. Probably won't like that. The reason I'm doing it this way is I'm going to have to stop it here in just a moment. It's going to go into an infinite loop, and I'm probably going to see a lot of here's. Maybe. We'll see. So I've got a here. Okay, so it's the first time we're here. And I think this is right. So this allocation sub recycled allocation to grow, that's going to be a pointer. Yeah. And obj is a T star. Okay. That all looks correct. This unlock. Sorry, this should have been right here, right before the this unlock. That's what I'm, nope, right here. I want to say cout unlock inline, and the only reason is so that I can what's it not liking? What did I do? Did I break something? Probably did. Okay. So at this point, yes, probably a modern debugging tool would be faster. I just am not that good with GDB. So we got here. Wait. Did it not rebuild? Cut it off too soon. Okay, we got through the unlock twice. Oh wait, nope, that's in a different. Okay, we hit the unlock once. That shouldn't need to make all of those. Test singleton object pool. I don't think it needs the target. The answer is no, it does not. So the only reason I'm doing that is so now I can say make clean, make just the one thing, and it shouldn't need libtang. Do this again. There. Now it should be able to make it without having to go through the entire rigmarole. Sorry, just a slight quality of life improvement. Still don't know what's going on, though, with the test. So at what point are we dying is the question. So I'm going to do this. All right, and let's so we made it through 6, and we're dying at the get after So wait. So we've got our pool, that's fine. We're getting object A. We recycle object A. We get object B. And we're just making sure that they're the same. We're getting object C. So this should give us, okay, I want to think through this again. Get A, recycle A. So recycle has 1. Get B, and A and B should be the same thing. So there's nothing left to recycle. So then we do another get, and we never come back from that. Okay. So it is in the get. When we do the first get, current recycled allocation, if it does not equal -1, that is true. We figure out which recycled allocation we're in. 0, presumably. And we get the temp, which is the current recycled index, minus minus. Is that right? Current recycled index. So the first time we recycle is wait, let's go back. When it's instantiated, current recycled index is grow -1. We recycle, and it increments that. And if it's equal to grow, recycled index is 0. That's fine. And current recycled allocation will become 0. Okay, 0 and 0. Now, get, first time, allocation does not equal -1. So we go in here, sub 0, sub grow. Then we say recycled sub 0. That should be fine. And now if the recycled index is less than 0, then we decrement the recycled allocation, and this should equal grow. Still dying on 6. Oh! I've got to return the lock. Yeah, mutex. That's why. It was hanging. That's just said there's no loop. I thought I'd already checked the locks. I just didn't say anything. Segmentation fault after 8. All right. That's always fun. What is 8? When we recycle object C. So, what we're going to do is we're going to say cout this current recycled allocation. This current recycled index inline, but nope. Let's indent this just a little bit. Okay. Maybe it should be the -1. Maybe I was wrong to change that. I was wrong. And this makes plenty of sense. We'll see it go all the way up to 2000 because that's one of the tests. Anyway, all right. So let's clean this up, shall we? Remove that there. Did I not write that? Okay. That's always good. Let's go for the big one. Make clean. Make test watch. And if this works, we'll delete the old comments. And we'll finish up for the day. Everything passes. So, what was the point of all of this? I'm glad you asked. We got rid of memory allocations when we were freeing memory. And that means, can we label it no throw? Maybe. I need to check more on the no throw stuff. I don't know much about it, to be honest. So we'll have to delve into that more later. So this one can go away. This there's one. I'll just make sure I got everything. The make file, I'll include it with it because it's dealing with the SingletonObjectPool test. That all looks correct. And then the last thing is we will, on the include of Tang, there should be even though it was said under garbage collector, it was really SingletonObjectPool. All right. And just make sure that I'm not doing anything. Yeah. And what are we committing? Singleton object pool refactor to not need realloc during recycle. All right. We deleted more code than we inserted. I guess that's a good thing. We simplified the recycle, that's why. And now, did I, I can probably just do make docs PDF. For episode, anybody know what episode it is? 44. For episode 44. Not a big change in lines of code, but some good refactoring. One efficiency thing with the, first moving our code around in our garbage collected object, and so that stuff is actually in the .cpp file, and added our check to say, do we actually need to copy you? If I'm calling for a copy, do I need a copy, or can I just leave you as is? And then the singleton object thing, removing memory allocations. So, yeah, overall, I think that was really well done in terms of it was a good amount to get done. And it went a little longer trying to track down the memory bug. Not a memory bug, it was the locking bug. I messed up there. But all in all, a good run. Once again, thank you for joining me. I hope that maybe learning something along the way, and it's been worth I hope it's worth your time. That's the easiest way of saying it. All right. Well, thank you, and as always, have a great day. Bye.